Thank you very much. Thank you for being here amongst all these wonderful distractions that we have at New Scientist Live. I'm especially grateful that you're here because this is going to be a terrible talk. And it's going to be a terrible talk for three reasons. Firstly, one of the first rules in science communication is that you don't show people graphs. People like pictures, we like videos. I just noticed when they were running the trailers, there were very few graphs up there. I have, I think, 3 graphs in the talk, and one of them is the most exciting slide. So I will point it out, and you can be excited by it when it comes up. You're a New Scientist audience, I know, so I think I might get away with it. Secondly, one of the first rules of science communication is to talk about other people's work. Usually as an astronomer on the sky at night or on a stage like this, I get to say the word we a lot. So for example, last year we sent a probe to Jupiter, and it's now flying over the cloud tops and sending back amazing pictures. And by we, I mean either astronomers or the human race. Or, you know, we've built a machine that allows us to detect gravitational waves. This talk has a large chunk of my own work in it, which means I have to give you the details rather than the headlines. And thirdly, this is a talk about a subject where I don't actually know what I think. I want to talk to you about the possibilities of alien life out in the universe and what it means that we haven't yet detected aliens. I suppose the fourth reason this is a bad talk is that we haven't seen any aliens yet. So this talk doesn't have a punchline or an ending. So when we get near the end, I will artificially make a spectacularly overreached prediction to make it feel like there's a conclusion. So as long as you're okay with all of that, I guess you're in a venue you can leave, let me start. And I want to start with this. This is, of course, a picture of the night sky, and this is why I'm an astronomer. I am, unlike some of my colleagues who are sort of escaped mathematicians or physicists, I'm somebody who grew up as a small kid looking at the stars. I grew up in Devon, and I would go out with my telescope, which I'd sort of scraped together money to buy, and I would try and discover things. I was particularly excited in discovering comets, because comets are named after you, and Comet Lintot, I think, I still think that sounds pretty good. But I'd settle for an asteroid or a supernova or something like that, but it became apparent pretty early on that I wasn't going to discover anything with a small reflecting telescope of the kind you could buy with money from a paper round. And so instead, I used to just stand outside, let my eyes get used to the dark, and I'd look up at the night sky, and I'd do 2 things. One was I'd look for aliens. Because I was also growing up watching Star Trek on television with the Star Wars films, reading as much science fiction as I could get my hands on, mostly in trashy old paperbacks. And what I learned from science fiction is that we had a future and possibly a present in which any remotely intelligent race gets its act together and starts sending spaceships flying amongst the stars. Civilizations spread from one solar system to another with vast engineering projects as new settlements are established on new worlds. There's these grand stories, sometimes optimistic, sometimes pessimistic, that you get in science fiction. And yet they were all about a cosmos teeming with intelligent life. And so it seemed to me, and it still seems to me, that if that's the universe that we live in, alien life should be obvious in the universe. And I'll talk a bit in a sec about how astronomers have tried to look for it. But as a kid looking at a vista a bit like this, I just thought you should see the spaceships. We should see stars blink out as space stations are built around them. We should see galaxies light up as there's that night flash when a spaceship goes into warp drive. And I couldn't see any of those things with my eyes or with my telescope or in my reading. And so the second thing I'd do is I'd wonder whether there were planets up there in the night sky. And we now know, as I'll say in a second, that when you look at a scene like this, you see gas, you see dust, you see stars. And we now know that most of the stars that we can see in the night sky have planets going around them. It's the great revelation of astronomy that sort of crept up on us over the last 10 years. We've gone from wondering whether there are other worlds out there, places to set our science fiction stories on, to a world, a universe in which planets are really common. And that makes the first problem worse. If there are worlds out there, then there must be places for life to exist. And if life exists, why are we not seeing spaceships zooming around the cosmos? And it's not, I learned later, not from lack of looking. It's not that astronomers are bad or worse, that we're keeping the stories of alien life from you. I want to be clear that there's no conspiracy theory. Most of the astronomers I know can't keep a secret about anything. I promise we're not hiding the evidence of alien life, but we have looked and we haven't found anything. Mostly, we've done that using radio telescopes like this one. This is Parkes, this is the Dish in Australia. One of two telescopes that's currently spending about 20% of its time doing a dedicated search for alien life, for the radio signals that we expect to be associated with intelligent life in the cosmos. We use radio because it's easy to broadcast over large distances, and there are both deliberate signals we might look for, but also maybe the accidental emissions from things like airport radar or something on an alien planet. And there's a project called Breakthrough Listen, which has bought time, purchased time on these two telescopes, this one and one in West Virginia in the States, to do this search for alien life. And they've found, well, if you listen to the Daily Star, they found alien shock as scientists reveal 11 mysterious signals hailing Earth are probed for UFOs. Not even sure the sentence makes any sense. This is the results of the first year of this search, reported more properly by New Scientist. We haven't heard from aliens, here's why we might never. That search, and in fact 40 years of searching for alien radio signals, has found absolutely nothing. So we have no definitive proof that there is alien life out there. Now, it may be, of course, that we're not looking hard enough, and I think we should keep looking, and that's aided by all the work that we've done to try and establish that there are planets out there. But there's this problem with radio waves. We used to think that you should definitely listen for aliens using radio waves. We had become, in the 20th century, a civilization that broadcast its presence out into the cosmos. We broadcast broadband television, for example. Back in the 40s, 50s, 60s, television became powerful enough that you'd expect to be able to detect it on nearby planets so that they'll be watching these alien civilizations, our television. It's been suggested that's why we haven't heard from them, but let's put that to one side for now. But actually, because technology has evolved, we've become radio quiet as a civilization. We don't waste energy beaming stuff into space anymore. We have targeted transmission to satellites. Our television is carried through fiber optic cables. So maybe radio waves aren't the way to go. And it's been suggested by astronomers like Paul Davies and others that we should just look for weird stuff in the cosmos. I'm going to use technical terms because you're awake, you've been all day. So weird stuff. Whenever you see something unusual in the universe, various of my colleagues say, well, we should take this seriously and understand whether this is evidence of alien life or not. And I thought this was an interesting idea, and then it happened to me. So my day job isn't looking for aliens or even thinking about any of this stuff. My day job is trying to understand objects called galaxies, things like this. These are two nearby galaxies. The one on the left here looks a bit like the Milky Way. The one on the right looks like a big ball of stars. It's an elliptical galaxy. Each of these systems has about 100 billion stars in it, and they're different, and you can see that they're different because their shape is different. Now, one of the things I do want you to take away from this talk, which is very different from the talks that have been given on the stage all day by some of my wonderful colleagues, I want to come clean with you and point out that astronomy is a really simple science. Okay, I know we have an excellent reputation. We've got 100 years of propaganda that makes you think that if you're an astronomer, you must be clever. But astronomy is really easy because the stuff that we study is a long way away. And so we can't really do much with it. If you want to understand stars, well, you have a brightness. Is it a bright star? Is it a faint one? And you might have a color. Same with galaxies. If I want to understand a galaxy, I can only make simple measurements. I could say, how bright is it? Well, that tells you how many stars there are there. I could say, what color is it? That tells you what kind of stars are there. Big blue stars are young, so if you see this blue galaxy on the left, you know it's formed stars recently, whereas this red galaxy over here hasn't had any recent star formation. And you've got the shape of a galaxy. And the shape of the galaxy tells you how the stars are moving, and that tells you whether the galaxy has interacted with its surroundings. It tells you whether it's merged or collided with other galaxies. So all you need to do to understand galaxies is measure their brightness. We can do that automatically. You measure their color. We can do that automatically. And you measure their shape. And to get the shape of a galaxy, you need people. You need to look at the galaxy and say, look, this is a beautiful spiral galaxy. This is an elliptical. And 10 years ago, we decided to ask people like you, ask the public to help us do this. Because we had so many galaxies that we couldn't possibly do this ourselves. And we launched a website called Galaxy Zoo. This is how it looked 10 years ago. This is cutting-edge web design. If there's anyone who works on the web today, it's got frames, which gave you a galaxy and asked what shape it is. And hundreds of thousands of people over the last 10 years have helped us sort through galaxies. So that's the day job. But we realized that if people were willing to look at galaxies, most of which, frankly, are small, blobby things, then maybe people would be willing to do other stuff. Maybe they would help other scientists. And so we built other projects. And so if you go to Exoplanet Explorers, for example, .org, then you can help us find planets around other stars. And this doesn't involve looking at pictures of planets. I'd love to be able to show you pictures of extrasolar planets. Somewhere sitting in the audience is the producer of The Sky at Night, who just told me that we can't make a program about exoplanets until we get pictures of them back. He's not as excited about graphs as I am, and we're working on him, and we will get through this. But I can't show you pictures of exoplanets, not because the planets are far away, and not because they're faint, but because they're too close to the stars that they orbit. The stars are bright and the planets shine only with... The producer is now shuffling uncomfortably in his seat, by the way, so that's good. Don't worry, I won't point you out just yet. Anyway, this audience really likes graphs. I can tell. They're really excited for the graph to come up. Anyway, the stars are so bright that you can't see the planets next to them. It's like trying to pick out a glowworm in front of a stadium floodlight. And so we have to find indirect methods of measuring the brightness of these planets. So we can do that. Here, for example, is the sun. And this is a video of the sun on a particular day a couple of years ago where Venus got in the way of the sun. And so Venus is the black dot that's moving in front of it. And on the right there, that's the first of the three graphs. It's not the exciting one. But this graph just shows the brightness of the sun over time. You can see when Venus is in the way, there's a dip in brightness. Now, we know what's causing that because we can see Venus on the picture. But if all you were doing was measuring the brightness of the sun, you'd be able to deduce that Venus was there because there's this dip in brightness. And if you wait long enough and you're in the right position, then Venus will orbit the sun, and there'll be another dip, and the sun will seem to be blinking. And from those blinks, you can work out that planets exist. And so that's what we did. We've put graphs like the one on the right online from a NASA space telescope called Kepler, and we asked the public to sort through them and find planets that would otherwise be missed by computers. And people did that. Here, for example, is a guy called Andrew Gray. He's a car mechanic in Darwin in Australia, and he was one of the discoverers of a 5-planet system. So a system of 5 planets going around a star called K2138, which is a terrible name. Andrew's fabulous. He was really enthusiastic about his discovery. He happens to be an amateur astronomer. And when he was interviewed by the local news, who were very impressed that somebody from their town had found a 5-planet system, they said, what are you going to do to celebrate? And Andrew said, well, looks like it might be clear tonight. I'll probably drag the telescopes outside and have a beer with them. which I think is the most Australian way to celebrate discovering a planet I could think of. And the system that Andrew discovered, this is completely irrelevant, but it's fun. This is the difficulty about talking about your own work. This is the K2138 system to scale. It's got 5 planets, which we've called B, C, D, E, and F. Luckily, nature has arranged them in alphabetical order, so that's exciting. See, not all audiences laugh at that. That's good that you got that, because normally people have stopped listening by now. Guy in the front row thinks it's really funny. This is good. Keep it up. Anyway, B, C, D, and F. And what's cool about these planets is they form a particular pattern. So for every 3 times, they're all closer to their star than Mercury is to the sun. They're packed in there. And for every 3 times B whizzes round its star, I think it takes about 2.5 days. For every 3 orbits it completes, C goes round exactly twice. And for every 3 orbits C completes, D goes round exactly twice. And for every 3 orbits D goes round, E goes round exactly twice. And for every 3 orbits E goes round, F goes round exactly twice. And we've discovered a 6th planet I'm not allowed to tell you about because we haven't written the planet yet, but there's a 6th one out here that also follows the same pattern. And so we have this it's called a resonant chain of planets. And it tells us something about how these planets have formed. We can also turn them into music. So here's what happens if you take that planetary system. This is an animation by Matt Russo. And every time the planets go round, I'm going to make them chime, play a musical note. And the reason that sounds nice to listen to, the reason that sounds musical, is because we're in this harmonic series. There's actually almost a perfect fifth between each planet. And using that music, I can now segue to the impressive graph, most of which I've hidden for a second. So just because I'm going to push my luck, can we have some applause for the graph, please? Okay. Thank you. When I reveal the rest of it, I won't even have to ask. I'm going to tell you now you're going to applaud the end of this. So this is the brightness of a star. So it's exactly the same graph as the one I showed you with the sun. But this isn't the sun. This is the star KIC 8462852. One of my favorite stars. And you can see it was monitored by the Kepler Space Telescope. And just after we started watching it, this thing blinked. It caused a dip. Now, I asked new scientists for a laser pointer, but apparently they don't work. And I really want to make sure I'm pointing the right thing, so I get to wield a big stick. So you see this here? Just after we monitored, I'm so glad that didn't go through the screen. At this point here, the star dipped in brightness. Do you see that? And then a couple of weeks later, actually a couple of months later, it did exactly the same thing. And so this is really exciting. We've got a blink and then a blink. So that could be a planet getting in front of the star, and then going around and getting in front of the star again. And all we need to be able to publish this and claim a planet discovery around KIC 8462852 is a 3rd blink. And instead of that, this was found by our volunteers, by the way, on our website. And they were waiting for the 3rd blink, but nothing happened for about a year. And then this happened. The star faded. Don't applaud yet. Some of you went for it. This gets better. I know you don't believe me. How can it get better than this? But it gets better. The star faded by about 20% for about 8 hours. And then it came back to its normal brightness. And stars don't do this. In fact, I could quantify that. Kepler monitored 150,000 stars for 3 years, and not one of them did anything remotely like this. And then the star just carried on, shining away like nothing had happened until the end of the mission, just before Kepler stopped looking at it. Coincidence? Yeah. Basically. This is kind of amazing. I hope you're ready. This is what happened at the end of the thing. See? Yes, exactly. Look at this. You've never seen anything like that before. No star does this. It sort of went bonkers for a few weeks. It started turning on and off and shining and dipping and brightening. And this makes no sense whatsoever. Our volunteers, the people who found this star and said it was interesting, called it the WTF star. And we put that in the journal article. And then we got a letter from the editor that said, thank you for your interesting paper on this mysterious star. it's our policy that all acronyms have to be spelt out in full. And so WTF stands for Where's the Flux? Because that's what's happening here. Why is the star fading? It's a crap joke, but never mind. And in the paper, the most embarrassing thing about the paper wasn't the joke about the name. The most embarrassing thing about the paper was that we didn't have a decent explanation for this. Stars don't behave like this. It's not a planet. Planets don't change in size as they orbit. We thought maybe it might be dust around the star, but you can test for that by going and looking with an infrared telescope. Dust shines brightly in the infrared, and there's no infrared luminosity here. And so the best guess in the paper, we said, this isn't a planet, it's a stream of exocomets. So exoplanet is a planet around another star, and exocomet, a word we invented, is a comet around another star. And we said maybe there was a big comet, and comets are just made of ice and dust and dirt, and often when they're near their star, they break up. And so we said, okay, there's a comet, and as you can see from this really realistic artist's impression, it's broken up, and so you have a string of cometlets, another word that I've just made up, ranged along the orbit. And so you have one comety bit here, and then another comet bit, and then a big bit, and then here's the bulk of the comet over here. Now this is cheating, because you'll have realized that I can explain absolutely anything with this hypothesis, right? Because I can arrange my comety bits however I like to explain anything in the light curve. And actually it's worse than that. When we published the paper, we started to hear from people who have actually studied comets, which is not us. People who did things like land little Philae, this little space probe over here, that landed on comet Churyumov-Gerasimenko a couple of years ago. And they said, look, this isn't going to work. Churyumov-Gerasimenko is a typical comet. It's about the size of London. This is a very menacing slide. I want to point out this is an artist's impression. If you go outside and look up, you're not going to see this thing hovering off to the west. But comets are small, that's the point. It's only a few kilometers left. To explain our dips, because so much of the star's light was blocked, you need a comet the size of Ceres, the largest asteroid in the solar system, and it needs to have broken up, because they won't last very long, these comet bits. You need to get the biggest comet that's ever been seen by a factor of 10,000, and have it disintegrate just as you start looking at this star, and this has to be rare because it's only happened in one of 150,000 stars. So we were told pretty firmly that we shouldn't anymore consider this comet hypothesis, because we understand comets, and it's not a good fit for what we know about comets. And at this point, we started talking about aliens. And we started talking about aliens because I was in my office, and the phone rang. And it was a journalist, a friend of mine, somebody I've known for years, who said, Chris, I hear you've discovered aliens. And it was a Monday morning, and I'd had a coffee, but I think I'd remember that. And I said, I don't think so. Checking my email, searching for aliens to make sure I haven't missed an email from somebody on the Friday. But what had happened was our astronomers in the States, at Penn State and elsewhere, published this paper. I forgot to say, not only am I showing you graphs, I'm showing you the abstracts of academic papers. But this one's exciting because of one word. It's got the word megastructure in it. So this is a search for extraterrestrial civilizations with large energy supplies, paper 4. I assume you've read the first 3. The signatures and information content of transiting megastructures. And it turns out that you don't get to use the word transiting megastructure without the press noticing. And this is the kind of thing they had in mind. And the argument is that if you're an advanced civilization, you need as much energy as you can get. And even if you covered the Earth in solar panels, you'd be wasting most of the energy. What you should do instead, if we're serious about this, is go and dismantle the planet Mercury, use all of that material to make solar panels, and put them in what's called a Dyson swarm or Dyson sphere around the Earth's orbit, trap all the light from the star. I don't really have a good analogy for this, but I did the calculation on the way here. If you did that, you would get, with current technology of solar panels, so I'm not even assuming that an advanced alien race that can go and destroy a planet and make solar panels out of it does any better than we do at making solar panels, you get 3 yottawatts of power, which is, yotta is 10 to the 26, so that's 100 million billion watts. I don't have a good analogy. If anyone thinks of one, come and tell me, but it's the UK power consumption for the next 17 billion years, every second. So this is quite a good idea, right? You should probably do this. And so Jason and co said, well, that's what's happening. These guys have clearly started building this. And they've got little bits of solar panels, and then big bits of solar panels, and then there's the main fleet that blocks out your star. And it's not that much stupider than our comet proposal, right? In all seriousness, the argument against this is that it's an unscientific proposal, because you could arrange your alien space stations in any order that you want. But the same was true of our comets. The difference is that we knew enough about comets to be able to turn around and say, actually, that doesn't sound realistic, whereas we know nothing about what alien civilizations might build. And so this is an explanation of our data, which we can't explain any other way, which is well fit by a hypothesis involving aliens. It actually got worse, or better. This paper generated a lot of controversy, and people at Harvard went back and found images of this star taken over the last 100 years, and they found that the star is fading over the course of 100 years. It's actually 20% fainter now than it was 100 years ago. And so now I've got 2 weird things I can't explain. I don't know why it does these random dips, and I don't know why it's fading. Of course, if you believe in the megastructure hypothesis, they're just still constructing their space station. And you can predict that they're about 5,000 years away from finishing. So there's a prediction. In 5,000 years, this star will disappear. Actually, there are lots of ideas about what the star is, and we've managed, this is why it's a terrible talk, we've managed to rule out the fact that this is an alien megastructure. And here's the third graph, which is pleasing but slightly disappointing. So what you see here is that the star dipped again. We monitored it with robotic telescopes, and when it dipped, we followed it up with new cameras. And you can see here, this is a dip, this is date, this is last summer. And you can see there's this dip, the star gets fainter, but the colors represent different cameras. So the red one here is a camera that's sensitive to red light, and the blue one is sensitive to blue light. Astronomy is simple. And what you can see is in both red light and blue light, the thing faded, but at different amounts. So the red camera saw less of a dip than the blue camera. And what that means is this isn't a solid object, right? Because it's got a change of color of the light. So this is a cloud of dust or debris or something like that, not a solid alien megastructure. And just from experience, I know at least 3 people are going, well, what if they have lights on the outside of their solar panels? But if you work it out, you need enough power to run the lights that there's no point building the solar panels. So we can rule that out. So we haven't discovered aliens, and I'm left mourning my future where alien spaceships are really obvious, as sci-fi still teaches us they should be. And so what I want to do with the last 10 minutes, given my abject failure to discover aliens, is to try and think about why that might be and preserve the chance that there are alien spaceships up there, because it's much more vital than just satisfying an 8-year-old me's curiosity about the universe. I want, deeply, somewhere in my soul, for us to be the species that gets to go out and explore the cosmos. I don't think it will be our generation, but I want to think that in the far future, humanity will go out and explore the cosmos, and we'll be the ones zipping about in obvious starships and settling the galaxy. The problem with that is that I also think we're pretty rubbish. If you look around, humanity makes a lot of mistakes. We can enumerate them ourselves. And there's no reason to believe that we're special in the cosmos. And so those 2 things are problematic. If life exists everywhere, if on all of these planets that we've discovered, life gets to the point where it can behave like us, it can launch spacecraft, it can begin exploring its own solar system, then the odds of us being the only ones to go from there to the Star Trek future are infinitesimally small. My only hope of predicting that for humanity, the only way I can scientifically be an optimist, is to say that we've already done the hard bit, that in getting to what passes for intelligence, our human civilization today, we've got to have already got past the hard bit. So maybe life is rare, or maybe planets where life can exist are rare. So let's just think about that for a second. I'm going to assume that life needs roughly the conditions that exist on Earth. Mainly that you need liquid water and a solid or icy surface. I think we could question those assumptions, but at that point you're into Sagan territory and you're thinking about floating jellyfish in the clouds of Jupiter, which are brilliant, but it's very hard to think with. So let's assume we're looking for life like us. Do planets like our own exist? Well, a typical planet of the ones that we've discovered so far doesn't actually look much like the Earth. It might look something more like this. This is HD 209458b, artist's impression, not picture. Sorry, Sky Night. This is a Jupiter-sized planet that's so close to its parent star that it's evaporating. It's only 1 million miles from a sun-like star, and its atmosphere is boiling away. So most of the planets that we've discovered are hot. They're much closer to their stars than the Earth or even Venus or Mercury are to the Sun. And so you might say, okay, so maybe planets like our own where you can have liquid water are rare. But when you think about it, it's not surprising that most of the planets that we found are hot. Remember, we're looking for blinks when planets get in front of their parent star. And we have other methods as well, but they all share a characteristic in that it's easier to find planets that are close to their star. Give you one reason. If you're going to wait for a planet to go round and complete its orbit to see another blink, if it whizzes round every 5 days, you just have to watch for a few weeks and you get plenty of evidence that the planet exists. If you want to find an Earth-sized planet in an Earth-like orbit, you have to wait a year between each blink. And we haven't had the patience or the sensitivity to do that yet. So most of our planets are hot, but that's because of the way we make our observations. And we have found systems that have Earth-like planets. There are lots of them. Some of them NASA have even started making posters for. This is what it might look like to be on TRAPPIST-1e, discovered planet. This is a planetary system discovered by a Belgian team who named their telescope after the beer, which is excellent. So TRAPPIST-1, I don't know what alien life would think of that, but let's hope they like beer. TRAPPIST-1e is one of a 7-planet system in which 2 or 3 of them in the middle are habitable. And this is how big the neighboring planets would be. So 1D, 1E, and 1F are all potentially habitable. I particularly like the look of E, which has a 6-day orbit. They're very close to a very faint star. And so they can orbit happily and still be in what we call the habitable zone, the region around a star where we might have liquid water. And some of these planets, so we know these planets are common. A good estimate is that there are 17 billion of these in the Milky Way galaxy alone. So I can't get away with claiming we're special by saying that we're 1 in 17, that there are 17 billion other Earth-like planets. It's clear that there are plenty of homes for life. And it's possible that many of them have simple life. We're building telescopes now. This is I guess an architect's drawing of something called the European Extremely Large Telescope. It's the successor to the Very Large Telescope that we have at the minute. It was originally designed to be much bigger. It was something called OWL, the Overwhelmingly Large Telescope. But we've settled for extremely large for budgetary reasons. But it's a good name for it. The mirror is 39 meters across. We're building this right now. And in fact, the thing that's obviously St. Stephen's Tower with Big Ben in it next door, you can see there's some tiny astronomers arriving for work at the bottom there. The thing that really got me in understanding what size this was they've just signed the contract for the people to build the dome that this telescope's going to sit in. And the companies that bid normally build sports stadiums. So this is, think the Millennium Stadium or something like that with a retractable roof and a telescope sitting in the middle of the pitch. But this telescope and its instruments will be powerful enough to look at planets like TRAPPIST-1e, to look at planets around the nearby stars, and tell us by looking at their atmospheres if there is simple bacterial life on that planet. Because if you looked at Earth, you'd see oxygen, and you'd see an atmosphere which is out of chemical equilibrium, and you'd be able to say there's something very interesting going on here. Something's happening to maintain that atmosphere in the state to which it's reached, and you might suggest that that's life. And I think we're maybe 10 years away. There's also a European space mission called Ariel, which is UK-led, which will do some of the same job, to try and look for the signs of life in atmospheres of nearby planets. And at that point, in 10 years' time, I wouldn't be surprised if we could go outside and start picking out stars in the night sky and say, look, these stars seem to have planets going around them that are suitable for Earth-like planets and which have bacterial life on, at least. Something creating oxygen in their atmospheres. But that's not as... I think that's amazing. I think it's inspiring. I think it should make anyone want to learn more about astronomy and go on. But it's not the same as starships. And it doesn't make us special. So, how can we be special? We can get rid of some of these 17 billion by thinking about the stars. Here's a pointless animation of the nearest star to our own. I don't know if this has got sound. If it has, you should kill it. This is the nearest star to our own, Proxima Centauri. It's a small red dwarf, and it's got a planet orbiting it, we think, Proxima b. And Proxima b is on the edge of this habitable zone, sometimes called the Goldilocks zone, the region that's not too hot and not too cold, but is just right for our kind of life. But Proxima b is not a place I want to go on holiday, because Proxima, this small star, has violent outbursts. A lot of these small stars are unstable. They have giant flares which shoot out across the solar system. And if you lived on the surface of Proxima b, we think maybe every month you'd get a lethal dose of radiation from the star. So we have to worry about the star as well. And so some of the 17 billion planets will be around stars where the star is unstable. And that alone will make this not a useful place for life. But 17 billion is a big number. And even if we got rid of half of them, there are still plenty of Earth-like planets. And in fact, it turns out, after much debate, astronomers have decided that the Sun is a Sun-like star. So, in other words, stars that are about the same type and temperature as the Sun look pretty much like the Sun and behave like the Sun, which means they might have star spots, just as the Sun has sunspots, and they have flares and coronal mass ejections and all the rest, but they're not particularly dramatic. And we can assume that if life could get going on Earth, then maybe life could get going on these other planets. And so I'm left, as I promised you 40 minutes ago, without much of a conclusion. We haven't detected alien life. We've found lots of these planets, and yet we don't see obvious life flitting about the cosmos. And in fact, we've done ridiculous tests to see if sci-fi life, dramatic, galaxy-altering civilizations should exist. We've looked for signatures in distant galaxies. We've assumed that if you have a galaxy-spanning civilization, it should affect the light that we receive from the galaxy, because you see they gather so much of the sunlight, the starlight in the galaxy, and they emit it as heat, as radiation. That's what we do as life forms. That we've looked to see if there are galaxies that are excessively bright in the infrared that show signs of having their starlight captured, and we haven't seen anything. And so I also promised you a blatant attempt to invent a conclusion through a dramatic prediction. The real solution to this, I think, before I get to that, is blaming biologists, which is an excellent position for an astronomer to be in. Because I can tell you that there are places where life might exist, but we don't actually understand what it takes to get life started. And so maybe that process is impossibly hard. And maybe it's just that we won the lottery when life got started on Earth, and we were special in that way. Another possibility is that we don't understand what it takes to produce an intelligent civilization, even one at the level we are. I suppose we've got both gin and tonic and professional astronomers, which is my definition of civilization. And so we don't understand if you've got bacterial life or the very first stirrings of some self-replicating chemistry in the primordial soup or a hydrothermal vent, we don't understand how you go from that to where we are now. So maybe that's incredibly hard, and we've already won the lottery in getting this far. But blaming the biologists seems like a cop-out. We'll worry about them. Also, it makes astronomers less important. So here's my prediction. I think there's something special about the Earth. The optimist in me wants to believe there's something astronomically special about the Earth. And there's only one thing left, and it's this thing. This is a photo taken from the HiRISE camera on a NASA spacecraft of the Earth and the Moon. And it's not the best photo of the Earth and the Moon you can see in this exhibit hall, but it's special to me because HiRISE is a camera on Mars Reconnaissance Orbiter. And so this is a picture of the Earth and the Moon taken from Mars by a craft that we sent there. And it's here both because I think that's the pinnacle of our human achievement, but also because the Moon is special. There isn't another large planet in our solar system, and Pluto isn't a planet that has a moon. I can argue about that with you later. That has a moon that's large, and it does things for us. It creates tides. It creates environments that are land and water, where evolution perhaps drove the advent of animals and life on land. But also it keeps our axis stable. It means that the Earth doesn't wobble. Mars lacks a moon, and it wobbles on its axis over millions of years, causing dramatic climate variations. And so out of nothing but sheer optimism and a desire to end the talk on something that sounds like a conclusion, I'm going to predict that there will not be planets that we discover in the next 10 years that have large moons. People are out there looking for them right now, looking for the signatures in those blinks that would tell us that there's a moon around a planet, but I don't think they'll find them. I think that if we believe that the moon is special to us, and there are arguments that we can make that show that it is, then we can explain that we are the species that will have the cosmic destiny not to destroy ourselves in the near future, to head out into the cosmos and live the sci-fi future that I dreamt of when I was a kid. And I really hope that's us. I'm going to pin my hopes on moons being rare, and I'm going to look really good in about 10 years if this turns out to be true, and really stupid in about 3 months if they announce the first exomoons. Thank you for listening. Talk to you soon. Thanks.